Have a look around you. I mean, right now. The chair you're on, the air you're breathing, the device you're watching this on, it's all made of the same basic stuff. Today, we're diving deep into what that stuff, matter, really is.
So let's kick things off with a little riddle. What in the world could possibly connect a gigantic burning star, a plain old stone, and one tiny drop of water? At first glance, you'd think nothing, right? They seem like they're from completely different worlds. But they share one deep, fundamental connection.
And the answer is, they're all made of matter. Yep, that's it. That's the secret ingredient of pretty much our entire universe. Everything you can see and touch and feel is just matter, arranged in a bazillion different ways.
So what's the official definition? It's actually super simple. Matter is just anything that has mass, the amount of stuff packed into it, and takes up space, which means it has volume. If you can weigh it and it takes up room, well, you're looking at matter. Now this question, what is everything made of, is ancient. Seriously. Philosophers in ancient India and Greece were wondering about this thousands of years ago. So today, we're going to be detectives and follow the clues from a modern investigation to see if we can crack this thing once and for all. For the longest time, there was this huge debate with two main camps. One group thought matter was continuous, like a block of wood that you could just keep cutting into smaller and smaller pieces forever. The other group thought it was particulate, made of tiny individual bits, kind of like sand. So which one is it? A solid, unbreakable block, or a collection of tiny, tiny pieces? To solve this, we need evidence, and our first big clue comes from an experiment so simple you could do it in your kitchen. This is where the whole mystery really starts to unravel. Okay, picture this. You get a glass of water and mark the water level with a pen. Then you pour in some salt and stir it up until it all disappears. Now, common sense says the water level should go up, right? I mean, you added something to it. But here's the crazy part. It doesn't. The level stays exactly the same. So, where did the salt go? It didn't just vanish. It actually slipped into the tiny, empty spaces between the water particles. And just like that, this one simple trick proves matter isn't a solid block. It has to be made of little particles with gaps between them. The particulate team was right.
All right, so we've cracked the first part of the case. Matter is made of particles, which of course leads to the next big question. How small are we talking? Like microscope small or something else entirely?
To try and wrap your head around this, get this. If you take just a couple of tiny purple crystals of a chemical called potassium permanganate, they can turn 1,000 liters of water a light pink. 1,000 liters. But it gets crazier. If you take some of that pink water and dilute it again, it's still colored. You can do this over and over. That can only mean one thing. Each of those original tiny crystals must contain millions upon millions of even tinier color particles. I just love this quote from the source material because it says it all perfectly. The particles of matter are small beyond our imagination. I mean, just think about that. It's an absolutely mind-bending idea. Okay, so we've established that everything is made of these unbelievably tiny particles. But what are they actually doing? Are they just sitting still? Oh, not at all. They are in a constant wild dance, and they follow a very specific set of rules.
And here are the 3 big rules for this particle dance. Rule 1, as we saw with the salt and water, they have space between them. Rule 2, they are constantly moving, jiggling, and vibrating. And Rule 3, they attract each other, like tiny magnets. Space, motion, and attraction. These 3 rules basically explain everything.
So this never-ending movement, that's what scientists call kinetic energy. And here's the cool part. Temperature is basically just a measurement of that energy. When you heat something up, you're not really adding heat. You're just giving its particles more kinetic energy, making them dance and move around faster and faster. And all that movement causes something called diffusion. Diffusion is why, when someone is cooking something amazing, the smell eventually finds its way across the entire house. The food particles are literally dancing their way through the air particles to get to you. And since heat makes particles move faster, this happens way quicker with hot food than with cold food. So what happens when you put all these rules together? You get this constant battle between the particles' motion trying to fly apart and their attraction trying to pull them together. And that tug of war is what creates the 3 states of matter we all know and love: solids, liquids, and gases. It all comes down to who's winning that tug of war. In a solid, attraction is winning, big time. The particles are locked in place, giving it a definite shape and volume. In a liquid, it's more of a tie. The attraction is weaker, so particles can slide past each other, taking the shape of their container. And in a gas, motion wins hands down. There's almost no attraction, so the particles just fly around freely, filling up whatever space they can. A really great way to picture this is with our particle dance metaphor. Solids are like a tight huddle, where everyone is vibrating in place but can't really move. Liquids are like a crowded ballroom. People can slide and move past each other, but they're all still pretty close. And a gas? Well, that's just a chaotic mosh pit, with particles bouncing off everything in sight. And here's where it gets really fun. Since the states of matter are just about how particles are behaving, we can actually change them. By adding or taking away energy, we can make matter the ultimate shapeshifter, forcing it to change from one state into another. Let's just follow the journey of water. You start with ice, a solid. You add heat, and its particles start dancing more wildly until, at the melting point, they break free and become liquid water. Keep adding heat, and they'll start moving so fast that they fly apart entirely. At the boiling point, escaping as steam, a gas. But there is a really weird thing that happens here. While the ice is melting, or while the water is boiling, the temperature actually stops rising. It gets stuck, even though you keep pumping in heat. So where is that energy going? It's being used for a very specific job. It's called latent heat, and it's the hidden energy needed just to break the forces holding the particles together so they can change state. I love how our source material says the energy literally gets hidden inside the beaker. It's not making the particles dance faster. It's being spent on the hard work of breaking up that tight huddle to create the ballroom, or clearing out the ballroom to let the mosh pit begin. And get this, sometimes matter takes a shortcut. It's called sublimation, and it's when a solid turns directly into a gas, totally skipping the whole liquid phase. The classic example is dry ice. It doesn't melt into a puddle, it just seems to vanish into a cloud of gas. And the opposite, going from a gas straight to a solid, that's called deposition.
So, what a journey. We started with an ancient question, dove down into the world of unimaginably small particles, and saw how their dance creates solids, liquids, and gases. Which leaves us with one final, huge question. Is that it? Are those three states all there is? Or are there other, even more extreme states of matter hiding out there in the vastness of the universe?